Welcome to the cosmos of discovery, where the boundaries of our understanding are constantly being pushed by new and incredible findings. Today, we're diving into a groundbreaking discovery made by the James Webb Space Telescope, the detection of an ancient black hole that's simply too massive to exist, according to our current understanding of the universe's early days. Strap in as we unravel the mysteries of this colossal enigma in space. Black holes in the early universe present a conundrum. Based on terrestrial and space telescope observations, we know that within a mere billion years following the Big Bang, certain black holes reached sizes a billion times greater than the Sun's mass. Yet, our existing models fall short in explaining this rapid expansion. This begs the question, how did these supermassive black holes form? This enigma has baffled astronomers for almost 30 years. However, thanks to the influx of new data from the groundbreaking James Webb Space Telescope, we're edging closer to an answer. In a recent breakthrough, the powerful James Webb Telescope captured the oldest and most distant black hole ever observed, consuming its host galaxy. This discovery marks a monumental stride in deciphering how supermassive black holes achieved masses billions of times greater than the Sun in the universe's infancy. Join us as we delve into how this latest discovery by the James Webb Telescope has illuminated the origins of these colossal, unseen mysteries of the cosmos. To comprehend this, it's crucial to recognize that black holes primarily grow in two ways: through steady, gradual accumulation of matter, including gases, and through singular events. Events such as galactic mergers and the engulfment of massive entities like stars, stellar remnants, and other black holes play a crucial role in black hole evolution. Typically, the primary mode of black hole growth over time is the gradual accretion of matter. However, growth can also occur in rapid surges, particularly during dramatic events like the merging of galaxies. This is especially true when two supermassive black holes, each originating from a merging galaxy, coalesce. When dealing with an accreting black hole, like those in active galactic nuclei or quasars, it's essential to consider the balance between the outward forces of radiation and winds emitted by the black hole and the inward gravitational pull of matter. If there's an excessive influx of matter, the resulting increase in radiation and winds can repel the incoming material, a phenomenon that happens when the growth of a black hole exceeds a specific theoretical threshold. Due to this relationship, there's a limit to how fast black holes can grow. Consequently, when tracing back in time, there's a boundary to the size that the initial seed of these supermassive black holes must have been, even for black holes with masses of tens of billions of times that of the Sun. The fact that today's black holes have reached solar masses in the tens of billions doesn't necessarily create a discrepancy. This is because these black holes have had approximately 13.8 billion years of cosmic history to develop. However, looking back in time, we might have expected the most massive black holes observed in the universe's early stages to be significantly less massive than the colossal ones we see today, with billions or even tens of billions of solar masses. In the era before the James Webb Telescope, it was quite rare to identify astronomical entities like galaxies and quasars from the universe's first 1.5 billion years, beyond a redshift of z=4. This difficulty arose because these objects were not only incredibly distant, but also fainter, lower in mass, and their light was significantly redshifted due to the expansion of the universe. The few we did find, if they exhibited sufficient activity at their centers, provided enough data to estimate the masses of their supermassive black holes, using information from the non-visible portion of the spectrum, such as infrared or X-ray wavelengths. Surprisingly, we started discovering that even before the universe was a mere 1 billion years old, some of these black holes already had masses comparable to, or even exceeding, those we observe today. The revelation that some black holes exceeded a billion solar masses soon after the Big Bang posed a significant puzzle. How did these black holes become so massive in such a short time? To reconcile this, with other existing data about the universe from observations of cosmic structures, galaxy evolution, the residual radiation from the Big Bang, and more. Three major hypotheses were considered. First, the possibility that the universe was initially devoid of black holes, with the first ones emerging only after the earliest stars lived and died, leaving black hole remnants from the most massive stars. Second, the theory that while the universe was born without black holes, they formed not just from stars, but also from dense clumps of matter like gas streams, which directly collapsed into black holes, creating event horizons around themselves. Third, the idea that the universe might have started with primordial black holes or incredibly dense regions, which rapidly collapsed to form black holes long before the first stars had a chance to develop. The first scenario is a certainty. As soon as the universe began producing stars, many of these first-generation stars would end their lives in catastrophic supernova explosions. The cores of these stars would collapse, and numerous of them would leave behind black holes. The remnants of these first stars, the black holes, would have masses about 100 times that of the Sun. The second hypothesis, supported by recent theoretical simulations by Mohamed Latif and Daniel Whalen, suggests the formation of much more massive initial seeds, possibly up to 10,000 or even 100,000 solar masses. The third option, while more unconventional, might need to be considered if even more massive initial seeds are required. To truly understand the early history of the universe and the origins of the heaviest supermassive black holes, we must rely not just on theoretical calculations, but on actual observations. To comprehend how these black holes emerged and grew so rapidly in size, two primary types of observations are necessary. First, we need to look further back in space and time, to the earliest epochs of the universe. This means observing galaxies from the first 0.6 to 1.5 billion years of cosmic history and measuring the masses of supermassive black holes present at these early stages. Second, for those galaxies where a black hole's mass can be determined, we need to conduct detailed measurements. This comprehensive approach will provide critical insights into the development and growth of these colossal black holes in the universe's infancy. In these galaxies, we aim to assess the mass of stars present and determine whether the relationship between the mass of the central supermassive black hole and the stellar mass mirrors what we observe in later periods. Typically, this ratio is about 1 to 1,000. We need to find out if this mass ratio remains constant over time or if it evolves towards a more balanced value. With this information, we can discern if the black hole to stellar mass ratio stays consistent, suggesting that these black holes originated from stellar seeds. Alternatively, we might find an abundance of what are termed overmassive black holes, indicating that these black holes originated from something more substantial than the remnants left by stars. Now, in the James Webb era, we've made groundbreaking discoveries of black holes from when the universe was less than 600 million years old, just 4.3% of its current age, or even younger. In fact, we've detected 3 black holes from this period. One significant example is the supermassive black hole in CR7 1019, with a mass of around 9 million solar masses, accounting for about 1% of the total stellar mass at that time. This black hole dates back to approximately 570 million years after the Big Bang. The black hole U8 zone, dating back to just 470 million years after the Big Bang, presents an intriguing case. Its mass is estimated to be between 10 to 100 million solar masses, with the stellar mass within its galaxy falling within a similar range. This suggests that the black hole to stellar mass ratio could be at least 10%, possibly even reaching 100% or more. Additionally, the most distant black hole identified so far, located in the galaxy Gien's 11, originates from a mere 440 million years after the Big Bang. Remarkably, this black hole is approximately 6 million times as massive as the Sun and appears to be consuming matter from its host galaxy at a rate 5 times higher than what current theories deem sustainable. Roberto Molino, a team leader at the University of Cambridge's Department of Physics, highlighted the significance of this discovery, calling it a giant leap forward for black hole science. He mentioned in a statement that finding such a massive black hole so early in the universe prompts a reconsideration of their formation mechanisms. Early galaxies, rich in gas, would have been like a feast for black holes. The rapid accretion rate of the black hole in GNZ 11 suggests that black holes might have the capability to grow much faster than previously believed. The black holes discovered in the early universe have been observed to grow at an astonishing rate, lending support to theories favoring smaller initial black hole seeds. The Eddington limit, a key mathematical formula, dictates the maximum rate at which an object like a star can accumulate mass without its emitted radiation, or luminosity, repelling that mass, thereby interrupting its growth. While black holes themselves do not emit light, being surrounded by an event horizon that traps light, their intense gravitational pull causes nearby material to swirl violently and heat up, emitting radiation. The faster a black hole consumes matter, the brighter the light from the surrounding region, known as an active galactic nucleus, AGN. Therefore, the Eddington limit also applies to AGNs, potentially limiting a black hole's rapid consumption of matter. The newly discovered black hole is drawing in matter from its host galaxy at a rate 5 times greater than the Eddington limit allows. Although brief periods of such intense super-Eddington accretion are possible, they are typically short-lived. The research team estimated that if this black hole had been feeding at this high rate for 100 million years, it would significantly challenge our current understanding of black hole growth and the constraints imposed by the Eddington limit. The team hypothesizes that this black hole may not have originated as a massive seed, but rather could have evolved from a lighter stellar mass black hole seed. This development is thought to have occurred between approximately 250 million and 370 million years after the Big Bang, rapidly growing to its current mass as observed by the James Webb Telescope 13.4 billion years ago. The researchers are quite confident that the intense feeding of this black hole plays a significant role in the characteristics of GNZ 11, a galaxy about 100 times smaller than the Milky Way and notably luminous. However, this voracious consumption by the black hole might also be impeding the growth of its host galaxy. Ultra-fast winds of particles ejected from around the feeding black hole are likely dispersing gas and dust from the galaxy's core. Since cold clouds of gas and dust are essential for star formation, this means the black hole's activity is effectively halting stellar birth, thus stunting the development of this relatively small galaxy. In addition to learning more about this particular black hole and its galaxy, the research team believes that the capabilities of the James Webb Telescope will reveal more black holes from the early universe. Specifically, they aim to discover smaller black hole seeds in the cosmic infancy, which could shed further light on the origins and growth of these enigmatic celestial objects. Molino emphasized that we are entering a new era with the advent of the James Webb Space Telescope. The significant leap in sensitivity, particularly in the infrared spectrum, is akin to moving from Galileo's rudimentary telescope to a modern one overnight. Before the launch of the James Webb Telescope, there was a notion that the universe beyond the reach of the Hubble Space Telescope might not be as intriguing. However, this has proven to be far from the truth. The universe has been unexpectedly forthcoming in revealing its secrets, and this is just the beginning. With the James Webb era now in full swing, we are likely on the brink of resolving long-standing mysteries about the early growth of supermassive black holes, which is an exciting prospect. In another thrilling development, the second image of the first black hole ever captured further confirms Einstein's theory of general relativity. This new image of the supermassive black hole at the center of the galaxy Messier 87 was taken by the Event Horizon Telescope on April 21, 2018, over a year after its first successful imaging. Like the initial April 2017 picture, this second image displays a luminous golden ring, representing matter swirling around the black hole, and continues to shed light on the fascinating nature of these cosmic giants. At the core of this luminous ring lies a dark shadow, aligning with predictions from Einstein's 1915 theory of gravity, known as general relativity. Kiichi Asada, an associate research fellow at the Academia Sinica Institute for Astronomy and Astrophysics, highlighted the significance of this discovery in a statement. He emphasized that a fundamental aspect of science is the ability to replicate results. The confirmation of the ring in an entirely new dataset is not only a major achievement for the collaboration, but also a strong indication that we are observing a black hole's shadow and the material orbiting it. This new image of the supermassive black hole validates the accuracy of general relativity, which posits that the width of Messier 87 should remain consistent as long as its mass remains largely unchanged. This finding reinforces the idea that a black hole's radius is directly linked to its mass. The image also shows changes in the brightness of the disk, attributed to turbulence in the matter surrounding the black hole, which is being gradually absorbed by it. The question now arises, what's next in our exploration of this supermassive black hole? It's important to note that the first image of Messier 87, along with the detailed analysis of the data used to create it, represents a groundbreaking step in black hole research, opening up new avenues for further scientific exploration and discovery. The initial image of the black hole in Messier 87 marked the beginning of a new chapter in black hole research, providing scientists with a novel laboratory to test the principles of general relativity. Scientists have indicated that the next phase in these studies involves gathering repeated observations of the supermassive black hole. The new image represents the first instance of utilizing data collected from Messier 87 post-2017 by the Event Horizon Telescope, EHT. The EHT received significant assistance in capturing new and enhanced images of Messier 87 in 2018, thanks to the addition of the Greenland telescope to its network. This telescope, completed 5 months earlier in the Arctic Circle, joined the array of antennas that form this Earth-sized telescope. This addition notably improved the EHT's image fidelity and expanded its coverage of the sky, especially from north to south. These repeated observations of Messier 87 have also enabled the EHT to test advanced developments in a field known as high-frequency radio interferometry, as well as in independent imaging and modeling techniques. Rohan Deol, a Ph.D. candidate at the Instituto de Astrofísica de Andalucía, commented on the significance of the Greenland telescope's inclusion in the array. He noted that it filled crucial gaps in the Earth-sized telescope, enhancing the EHT's observational capabilities. The EHT continues to monitor and collect data, offering invaluable insights into the nature of black holes and the validity of theoretical models. Following 2018, further observations of Messier 87 were conducted in 2021 and 2022, with the next scheduled observation by the Event Horizon Telescope, EAT, set for the first half of this year. Astronomers are particularly keen to observe the jet of material emanating from Mighty 7, a feature that was beyond the EHT's capability to capture 6 years ago. Thiel emphasized that the 2021, 2022, and upcoming 2024 observations, with enhancements made to the array, are fueling excitement to advance the field of black hole astrophysics. In other developments, NASA scientists have recently observed a remarkable cosmic phenomenon, a fossil created by a supermassive black hole eruption over 5 million years ago. Utilizing the X-ray multi-mirror mission XMM Newton Space Telescope, with support from NASA's Chandra X-ray Observatory, the team at NASA's Goddard Space Flight Center detected X-rays outlining cold gas clouds in the relatively nearby spiral galaxy NGC 4009. 145, located 13 million light-years away in the constellation of Centaurus. This gas appears to have been propelled through the galaxy by an eruption from its central black hole, which possesses a mass of about 1.6 million times that of the Sun. The central supermassive black hole in this galaxy, with a mass equivalent to millions of suns, is actively consuming surrounding matter, fueling the luminous galactic core known as an active galactic nucleus, AGN. The gas influenced by this black hole serves as the foundational material for star formation. These observations offer crucial insights into how supermassive black holes, which can attain masses billions of times that of the Sun, affect their environments and play a role in guiding galactic evolution. As stated by Kimberly Weaver, an astrophysicist and team leader at NASA's Goddard Space Flight Center, there's an ongoing debate in the scientific community regarding the process of galactic evolution. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions, updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.